Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. I'm a bit nervous about talking here, not the least because Christian's talk was so amazing, but this time last year I spoke, within a few hours a baby daughter had arrived and I'd been stuck in the MSR communications black hole. So I guess these things don't happen every time you come down into the MSR lecture theatre. So I'm going to talk about some work I did with my great PhD student, Thang, who's with us here today, on speeding up Gaussian process methods. I'm particularly interested in Gaussian process methods for time series and very interested in audio applications. So when I started working in this general area, I met up with David Mackay, and David Mackay said it'd be great if you could train your Gaussian process time series models on Zubin-Garamani speech and then have it synthesize realistic Zubin-Garamani speak out of the model. Unfortunately, that turned out to be a bridge too far. But what we did come up with was a method that was great at learning the statistics of time series such as audio textures, which are sounds like running water, crackling fire, howling rain and wind, and then generating synthetic examples that you really can't tell the difference between those and the original, although they'll have a very different pattern of falling raindrops or different pattern of crackles and things like that. So let me play some examples just to motivate why we're interested in these models. So here's going to be a whole batch of textures. These are all synthetic sounds from a model involving Gaussian processes. And there's no sound. Let me Okay, so each one of those little chunks was a little synthetic texture that we've trained this model, which has Gaussian processes inside it, on. And those samples can be really short. They can be 2 or 3 seconds. And then you can ask the model to go ahead and generate infinite amounts of new data, a bit like Christian's text examples. Let me just play that again. So these are water sounds to start with, 2 different running water sounds. This is a campfire, and then a bigger fire which follows. These are wind sounds which are a bit ropey. I think wind has frequency modulation in it, which we find hard to match. Rain we're really good at. This is snapping twigs. It's a bit different from the original, but I think plausible. And at the end, that's synthetic applause coming from the model. Okay, so that's all well and good, but what we want to do is we want to in order to do this under the hood, we're using Gaussian processes and we're using very, very long time series models. So time series which are several seconds in length with a relatively high sample rate. So the question is, how are we able to do that? And this talk is going to be about an approximation method that we can use in these models in order to make learning and inference, if we wanted to do inference in these models, to remove these textures, say from speech, really, really fast. And at the start, I want to point out a difference between the approach we're taking in this talk and the previous couple of talks before Christian's that also talked about Gaussian processes in a time series setting. So in order to point out the difference, I want to go back to this model. So here's a very, very basic model for a time series, x of t, that says x at time t is equal to lambda times x of t minus 1. You just weight the previous x value and then add some Gaussian noise on it. And in the previous 2 talks, we talked about one particular way of generalizing that first-order autoregressive process. It was to replace this linear dependence on x of t minus 1 with some general function f, and then put a prior on that function that was a Gaussian process. Okay, that's what those 2 talks did. And you'll notice a couple of consequences from that immediately. First off, the joint distribution of all the x's 1 to t in your big time series is now non-Gaussian because of the nonlinear function f. And it's still a discrete time model. So we're still sampling this at some regular sample rate. What I'm going to talk about in this talk, because it works a bit better for audio, is a different generalization of this process. So we could say that this autoregressive process puts a joint Gaussian distribution on all of the x's from time t through to time big T. And instead of parameterizing the Gaussian distribution in this way, we're going to say that the whole time series x of t is drawn from a Gaussian process with a particular mean function and a covariance function. So now any marginal of this time series is going to be Gaussian distributed, unlike before, and we've now got a fully continuous time process that would help if you wanted to, say, change the sample rates of your observations. So there's some nice properties coming from that. The reason why this is perhaps better for audio applications is because you need really long temporal dependencies in audio, and if you did that using this sort of model, you need a very, very high dimensional X space, and that can be tricky to handle. So, so this is the route we've taken. And as I said, we're using this for modeling time series like speech, possibly mixture with these textual sounds, which are easily 10 to the 5 to 10 to the 7 data points. And you probably saw on the previous slides that people presented that this has a cubic cost in T. So for these very long time series, that really is prohibitive. And we're using several Gaussian processes in this model for these textual sounds. So multiply this number by 10, 20, or 50 to get the full size of the latent space, which is in those models. So how are we able to do this? Well, what I'm going to first explain is if you use an off-the-shelf method for approximating GPs in this context, it's not going to work very well. It's going to fall apart catastrophically. And we're going to investigate the method that Yutien used in his talk in the nonlinear Gaussian process state space models, now in this different time series setting, and just sort of show you how well it performs. So here's some time series data here. X is a time index in this example, and we've got some noisy observations of it. And what we can do, we're imagining our goal is to fit a GP in this example to it. So you can see, if you squint your eyes, there's a mean function now going through all those points, interpolating between them, and some error bars around them. And we're gonna compare this full true, if you like, GP fitting to approximate ones. And in order to do that, we're going to measure how good the approximate ones are by their mean squared error in this task, predicting the underlying noisy function values. And if you run the full GP in this example, it takes a long time, several tens of seconds, but it gives you a very low standardized mean squared error. OK, so the approximation method that Yutien pointed out essentially works as follows. It introduces a pseudo-dataset, a smaller dataset than the original, whose purpose is to summarize the full Gaussian process posterior. And it wiggles around where it puts these data points in order to come up with, in some sense, the best matching approximate posterior to the true underlying posterior. So if you use a very small number of pseudo points, so here I've chosen 4, and this is showing the input locations, the locations at which it decides to put those pseudo observations, then the approximation to the true posterior is quite bad. It gives back this very smooth red line here. It picks up on the fact that this sort of sequence of observations here seems to be a bit lower than is typically the case, and this one here is a bit higher. But other than that, it hasn't got any of these fine wiggles. Now, of course, what we're going to do in a minute is increase the number of pseudo points here, and we'll see progressively better and better correspondence between the approximate solution and the true solution. The error in this case is rather large. So the mean squared error, as you'd expect, is rather high. Now, as we increase the number of pseudo data points in our little summarizing data set, you'll see that the approximating function gets bigger, as gets better and better matched to the original. So we've now got lots of pseudo inputs, and the standardized mean squared error is coming down and down and down until at some point we're reasonably well approximating the true posterior. And we could have continued adding more and more data points in, and it would have indeed converged on this point down here. OK, so now here's the rub. This sounds fine. Why can't we just jack up the number of pseudo points in our data set for these texture-like stimuli, and eventually we'll know we'll be approximating the true posterior that the original GP would have, and aren't we home and dry? Well, here's the rub. The cost of this algorithm, as pointed out by Yutien, is of order Tm squared. We're zooming ahead here. Sorry, sensitive clicker. so the cost is order Tm squared. So it's growing with the number of pseudo inputs in a squared way, as you'd expect. Now let's go and do a thought experiment. How many pseudo inputs can we get away with? Well, the time scale of variation in our original time series, I'm going to call that tau. And it's quite quickly varying. So tau's quite short in this example compared to big T, which is the duration, the overall duration of the time series. And the effect of each one of these little pseudo inputs that you add in to approximate your posterior is always local, and it has roughly an effect width of order tau. Okay? It roughly influences the function, depending on how you set the hyperparameters, in a little region which has length tau. And so that means, in order to well approximate the whole thing, we need to make sure we have enough pseudo points spaced roughly every tau seconds in order to get accurate approximation. And that means M needs to scale implicitly to retain the same accuracy with big T here. And so when you put this observation together with the scaling back here that M down now depends on T, you get something which is order T cubed again for the same computational accuracy. And we really haven't gained anything by these approximation methods apart from the constant which sits outside this order. So in this time series settings, that means that you really can't use these conventional pseudo-data point approximation methods because you keep on having to add in more pseudo-data points, and at some point it's just going to break and you're going to lose accuracy. So I'm going to tell you now very quickly about the intuitions behind our method, which is going to be faster than this version of doing things by a considerable margin, and essentially gives up almost no error as compared to the full GP. So we're going to design an approximation method which is bespoke for time series. It'll work great for time series. It'll work poorly for other situations. And you'll get the full benefits of using a full GP in a fraction of the time, orders of magnitude quicker. Now, in order to do that, I need to tell you about prior work, which this is going to lean quite heavily on. And the prior work was by Ed Snelson and Zubin, and it's called the fully independent training conditional approximation. And we're going to base a new method largely on this work. Okay? You can think of it working in a very, very similar way to the method I showed you on the previous slides. The previous slide showed generic behavior of a whole class of methods, which include the FITSI approximation. So how did Zubin and Ed come up with a way of approximating GPs? Well, they started with their GP to start with, shown here by a factor graph for the aficionados. And they started by augmenting that model with a bunch of pseudo-inputs. So these are our pseudo-data points we're just going to add to our GP. And they're going to be smaller than the full number of data points we're going to handle in order to eventually give us some computational advantage. So they have inputs here, which I've called X. Those are the things that were at the bottom of the previous diagram that we're optimizing, and outputs U. So here we go. We've augmented it, and we've placed a joint Gaussian process prior now over the U's and the F's, and everything is pairwise connected. So here's the joint Gaussian process prior. Now, in order to make computation more simple, we're going to remove some of the dependencies in this full GP, and that will lead us to efficient algorithms. So in particular, we're going to move all the direct dependencies between the function values, all of these direct dependencies through one another. All of the dependencies between the function values are going to be mediated by the pseudo-data points U at the top. Okay? So we just go in and remove them. And now we're going to calibrate this new model so that it's as close as possible to the original GP that we had. Okay? And the way we're going to do that is we're going to carry out a minimization of the KL divergence between our new model here, our new model here and our old model over here. So we're going to do KL old model to new model, and that lets us figure out what these new distributions here over our pseudo inputs and the relationship between the function values F and our pseudo inputs down here. Okay? And when you do that, it's a very unsurprising result what comes out. You find that the optimal distribution over the pseudo input prior here in this new model is equal to the original prior under the GP of the U's. And the conditional distribution of the F's given the pseudo inputs is equal to the conditional distribution in the true model. Okay, so you just retain the original distributions and ditch the direct dependencies between the F's. Okay, so that's all well and good. Doesn't work very well for time series for all of the reasons that we discussed before. So how are we going to extend that for time series? And the idea is to introduce some additional links that we're going to delete from this graphical model in order to make things chain structured. Okay, so we start in exactly the same way. We start with our original F's, our function values. We augment with pseudo inputs again in exactly the same way. And now we're going to remove some of the direct dependencies between the function values. So we're going to remove the direct dependencies in this example just like this in the same way as we did before. And we're also additionally critically going to assume that the U's at the top here are now chain structured. Okay, so we're going to remove some of the connections between our pseudo-data points that we added in this particular way. And similarly, we're going to then remove the dependencies between U's and F's, which are not in the same block. Okay? So by deleting links in this careful way, we've converted our original graph that was a joint Gaussian process over the pseudo inputs and the actual variables we observe into something which is chain structured. That seems like it's going to be a disaster, but inside each one of these U's and F's in here, we'll actually imagine having a whole number of variables. So it's not like there's a single U variable up here which is acting as a bottleneck in a time series. It's going to be a whole stack of states. Now, we just go ahead and calibrate the model in exactly the same way as we did before. So we take the original model that we started off with and then minimize a KL between that and the new approximate model, which takes this nice chain structured form. And that gives us the optimal way, or an optimal way, of setting the conditional distributions on the U's, how U at time t depends on U at time t minus 1, and the relationship between these function values and the underlying pseudo-data inputs. Okay, so this method for constructing a new model, so the goal here has been to construct a new model parameterized by pseudo inputs, which retains as much of the structure as the original model, but now is going to be amenable to computation. And the reason why it's going to be amenable to efficient computation is that we've now got a chain structured graph, and so we can do efficient inference using Kalman filtering and Kalman smoothing rather than having to invert huge matrices as we would in a normal GP. And what's more, in this particular setting, you can now have as many pseudo inputs as data points as if you want, because you're going to get computational gains by the fact that you just have to run Kalman filters to do your matrix inversion rather than having to invert it in the first place. So we can introduce more and more and more pseudo inputs as the length of our time series grows and grows and grows. So this is just summarizing exactly as we had before. These methods for approximating Gaussian processes are a bit odd in a way, because we're perhaps normally used to thinking about inference as going in and approximating posterior distributions in some way. And really what we've done now is we've written down an entirely new model which is calibrated to the original model, but in which learning and inference will have many of the properties and hallmarks of the original model. And in this case, the model is a linear dynamical system, but the parameterization is very, very strange, right? Because in each one of these relationships here between U at time t and U at time t minus 1, and the relationships between U and F, they're all parameterized in terms of the original parameters of our GP, the hyperparameters, the length scales, the noise values, and things like that. So it's a very weird non-linear dynamical system with parameters which themselves depend on the hyperparameters of the GP. Okay, so the complexity, as we said, is linear in time. It's d squared cost, where d is the average number of observations per block. But the critical thing really is this linear scaling on time now. And many of the same things would have gone through if it's not obvious if you had multi-dimensional time series. So I've only talked about unidimensional time series, but for instance in the texture work we have lots of Gaussian processes at each time point. Exactly the same things apply. And similarly, you don't necessarily have to use a chain. You could use a tree structure over your inducing inputs as well if you want to use spatial data or perhaps other sort of data from, say, geostatistics. Okay, so finally I'm going to show some results. I'm going to use an audio missing data imputation example. These are examples from the textual type models inferring here. These are missing sections of speech. And this is a single model that's been trained on lots of speech. And we've asked it to impute these missing sections of about 15 milliseconds each. And you can see that these textual models do a decent job of fairly long-range interpolation through these little regions of a speech sound. And now I'm going to compare what happens in a missing data imputation case when you use the trained structured approximation as versus these normal off-the-shelf methods. So at the top here is the original FITSI method. This is the same plots you've seen before with training time along the x-axis here and mean squared error across the right. You can see this is doing rather poorly, even in this case where we use 1,500 pseudo inputs. This is for a time series which is 40,000 samples in length. These are some other methods that I won't go into, one of which is the variational free energy method that UTN used that we showed to start with. Very similar to FITSI, as I claimed earlier. This is a sparse spectrum method. Oh, sorry, this is the variational. No, this is the sparse spectrum method, apologies, that approximates the spectrum of the process. Seems like it might be a good idea for audio. Does about the same as these other conventional methods. Here's something sensible to compare to where we've blocked up the time series into independent blocks. And then we're going to use the FITSI-based method to approximate each one of those blocks. And that actually does a bit better on these examples, but it would have horrible blocky artifacts because you've thrown out your time series structure and you said each block is independent. And this is perhaps what people thought would have been the most natural thing to do. It's a method based on a connection to stochastic differential equations. In our hands, we could only get it to run on 20,000 data points because it took too long. It is very, very slow. And if you compare that, so this is the frontier traced out by these current methods. And if you compare that to what we get from running this new train structured method, you can see that we're cutting down for the same approximation accuracy, for the same mean squared accuracy, we're cutting down the training times by at least a factor of 10 in this example here, and tracing out this frontier. These numbers that I've shown here are the numbers of observations associated with each block in the approximate method and the number of pseudo inputs in each one of these blocks in our use. And there are sort of sensible heuristics you can use in order to figure out how to set these things automatically. It's not like you need to run things multiple times to figure out what these numbers need to be. Okay, so the summary is you can use GPs even for enormously long time series to do funky stuff like generating synthetic textures and removing them from speech, but you need to use approximation methods. And if you are in a time series setting, these types of methods that I've outlined here, these chain structured and tree structured Gaussian process approximation methods, will get you all the benefits of a normal GP, but for a fraction of the computational cost, because it's ignoring very long dependencies in your GP, which basically are extremely, extremely weak. Okay, great. That's the end.
I actually have one. So did you take a look at the latent representations and whether they are semantically meaningful or have some interpretation?
For the texture stuff, you mean? Yeah, yeah, that's really hard. So the latent space is at least 100-dimensional. That's just the state of the latent variables. If you're talking about the parameters and other things that really govern the statistics, there are thousands and thousands of parameters in these things. So they're GPs on each frequency band, and then there's spectrotemporal modulation, which is introduced by another layer of GPs. So it's hard to do. We haven't found a good way of compressing that high-dimensional space in a meaningful way to discover what textures are near each other and things like that. But that would be definitely a fun thing to do.
Like a sudden change in the texture that you have in the sound. For instance, starting and stopping the applause, or changing between two different types of speech sound.
Yeah, so this model is gives out temporally homogeneous textures. So it can do sort of one type of, I guess you'd think of it in some contexts as non-stationarity, so that might be the claps in the applause example, or the pitter-patter of raindrops. It can learn those temporal statistics. You would need to put another layer on the hierarchy to do things like merge, to switch off one texture and bring on another. But you know, it could be done, and we have examples where we've played with pairs of textures in that way. Yeah, but you sort of imagine it's the bottom layer of your big hierarchical model that you could go and learn if you're doing that. So one more question up there. Yeah.
Can you show the data computation slide again?
Yep, I can do.
So from that slide, I think the method knows clearly what frequencies to show in there. So how do you deal with the spectral components of the observations? Do you tell the algorithm through the prior maybe that the process is band limited, or everything is learned from in the training?
Yeah, so this is inferred as you go along. So this is one underlying model, and you can see that the predictions it makes really does vary on what the previous context was of the little gap it's looking at. So in this one, it had lots of high-frequency wibbles, and it's learned that in this context, it's good to predict with high-frequency wibbles on your underlying smooth variables. And in this one, things are rather more slow. So it figures out what the local spectrotemporal statistics are in some sense, and then interpolates using those local spectrotemporal statistics. Yeah, so it's automatic.
Okay.